Consider this circuit where we have a three-port network, and this three-port network is known to us with respect to its impedance matrix, all of its transimpedance parameters, 9 of them for a three-port device. In this case, we look at the impedance matrix and all the elements are real, and this is certainly an academic problem in real situations. All of our transimpedance parameters are going to be complex, real and imaginary components almost certainly. The numbers here are simplified, though, to make our math easier later on. So again, this is a bit of an academic problem. Attached to each port of this three-port network, we have a different device, a short circuit, 1 ohm resistor, and a Thevenin source, which we will consider to be one device with one set of device equations. And the question that we are asking ourselves is what are the voltages and currents at each of these three ports? Can we determine these 6 complex values? It may seem that this is an impossible problem, given that we just have this blue box and we don't really have any schematic as to what's inside. We don't know what the devices there are inside, how they're connected together. We don't really know anything about the circuit schematic in that blue box. So how would we go through and do analysis to find the currents and voltages? That's our normal way of finding currents and voltages, after all, is doing a circuit analysis on an explicit circuit schematic, which we don't have in this case. But we have the next best thing, or perhaps even a better thing. We know the transimpedance parameters of this three-port device. If that three-port device is linear time invariant, then we can describe it with the transimpedance parameters. And if our sources are assumed to be time harmonic, then that is all we need to know to solve this circuit and determine the complex currents and voltages at each of those ports. So let's see how we might do that. First thing we do is write down the equations that the transimpedance parameters provide to us. From the definition of the transimpedance parameters, we can determine 3 equations. Each equation relates one of the port voltages to each of the 3 port currents. And of course, the coefficients out in front of these equations are the elements of the impedance matrix, the transimpedance parameters. And so this really is our device equation for that 3-port device. This consolidates all the knowledge we need to be able to solve this circuit with respect to that 3-port device. Now, we add up all of our unknowns. Notice there are 3 voltages and there are 3 currents. So there are 6 complex numbers. We only have 3 equations. And so these 3 equations by themselves are not sufficient for us to determine the voltages and currents. And when you think about it, this makes perfect sense. These 3 equations describe only part of that circuit, and that is a 3-port network. There are 3 other elements in that circuit, however. In addition to the 3-port network, there are 3 devices. One of the devices is a Thevenin's equivalent source. We'll consider that to be one device. The second is a short circuit on port 2, and then on port 3 we've connected a 1 ohm resistor. Each of these 3 devices have their device equations, which we add to the 3 equations we got from the 3-port network and its transimpedance parameters. So for the first device, this Thevenin's equivalent source, notice this is the device equation. This is the equation that relates the source voltage to the source current. Notice that we have written this in terms of V1 and I1, and so you have to be careful there to write KVL and Ohm's law and KCL correctly in terms of V1 and I1. And so if you look at V1 and I1, you see that V1 is 16, which is that open circuit voltage source, minus 1 times I1, which is then the voltage drop across that source resistor given the direction of positive I1. So everything is written in terms, again, of how I1 and V1 are defined. For the second device, it's a short circuit. That equation is straightforward and there's not any ambiguity involved with it. For a short circuit, we know the voltage across it is equal to 0. And of course, the voltage across that short circuit is the port voltage V2. So we say V2 is equal to 0. This is the second of our 3 device equations. And then finally, we have a 1 ohm load, a 1 ohm resistor on port 3. And of course, the equation that relates the voltage across that 1 ohm resistor to the current through the 1 ohm resistor is Ohm's law. Now be very careful here. All right, be very careful. When we go through and we write Ohm's law, we have to write it in terms, again, of V3 and I3. If we write this in terms of Ohm's law, we might say, VR is equal to 1 times IR. VR being the voltage across the resistor, the 1 ohm resistor, and IR being the current through it. But in that case, we'd write the normal Ohm's law notation, where positive current is defined as going into the plus terminal of that resistor. If we look at V3 and I3, we see I3 is positive when going into the port 3 of the device, which is actually coming out of the plus terminal of the voltage across that resistor. So because of that, we have to go through and add a minus sign in there. Essentially, we're applying KCL and saying that IR is equal to minus I3. I3 and IR are pointed in opposite directions, or the positive, what we define as positive, we're pointing in opposite directions there. So be very careful on the minus sign. This is a problem that students mess up over and over again and lose points in terms of going through and defining carefully the equations in terms of the voltage and current notations. Again, it's easy to quickly say, well, Ohm's law is V times Ri. Well, again, you have to go through and look at the definitions in terms of how V and I are defined in terms of positive values. Sometimes we'll find that V is equal to minus I times R, depending on how positive current is defined. And of course, in this case, this is one of those situations where the minus sign arises. So be very careful. At any rate, if we go through and we take these 3 device equations for the 3 devices attached to our ports, and we add them to the 3 equations that define our 3-port device, our original 3-port device using the transimpedance parameters, count them up, we got 6 equations, and that's good news because we have 6 unknowns. If we were mathematicians, we would put down our pencil at this point and move on to a different problem. But since we're engineers, we're going to go forward and find the numeric answers to this problem. If we look at each of the 6 equations, we'll note that 2 of the equations, for example, say something about the port voltage V1. One equation comes from the source at port 1, the other equation comes from the first of the transimpedance parameters, from the impedance matrix, that first equation. And so we can equate those 2 relations and come up with a combined equation. Likewise, for the voltage at V2. From the short circuit, we know it's 0, but also we know V2 is equal to this from our transimpedance parameters, and we can combine them into a second equation. And then finally, V3 we know is equal to minus I3 because of Ohm's law, but also from the transimpedance parameters, we know V3 is related to the other currents in this form. And so we can combine this into a third equation. So now we have 3 equations here that involve the 3 unknown currents. We've gotten rid of all of the unknown voltages. Again, there's more algebra to do here. 3 equations, 3 unknowns. I'll skip the algebraic details. Go through and do this for yourself and prove it. And what we find here are these are the results we get for the complex currents and voltages. Now remember, the currents and voltages, as I said, are all complex. It's a little bit confusing in this case because I had all the transimpedance parameters be purely real. They could be purely real. Generally, they're not. Again, we just sort of use those values to simplify the mathematics. But remember, when we say they're purely real, we're saying they're complex values whose imaginary parts equal to 0. Or we're saying they're complex values whose phase is equal to 0. And so we go through and we get our solutions and we find, for example, I1. We could say I1 is equal to 7, and that would be correct. However, that implies that for some students that this is maybe a DC value, but it's not. And these are a complex value of 7, a number that has a magnitude of 7 and a phase of 0. Likewise, if we solve for I2, we would see that we get a value of minus 3, not a DC value minus 3, a complex value minus 3. In other words, a complex value with a magnitude of 3 and a phase of minus pi. It says the oscillation of the current, I2, has a magnitude of 3 and a relative phase of pi, 180 degrees out of phase with respect to the reference. Likewise, for I3, 1 times e to the j pi. Well, another way to write this is minus 1, but again, I like writing it in this form because it emphasizes that we're talking about complex numbers that describe time harmonic oscillations, sinusoidal oscillations, its magnitude and relative phase. So we could go through and write these in terms of the real and imaginary part. That would be fine as well. We would have 7 plus j0 here, and minus 3 plus j0, for example, 1 plus j0 in this case. And so I try to do this to get you to be comfortable with this idea, or used to this idea, that all of our answers are complex numbers. We can write them in real and imaginary, or a magnitude and phase. Often in this class, I'll make the math simple so they come out to be something relatively straightforward, minus 3 or j times 2, as opposed to something of 27 minus j 32 or something like that. Keep again the math simple, or the arithmetic simple, I guess, in terms of the calculation, but don't lose track of the fact that these are complex numbers describing time harmonic oscillations.